Hey everyone, it's March 16th, day after the Ides of March, March 15th. Noted, I believe, for the day Caesar was killed by his colleagues. We're starting, this is statistics, intro to stats, map 21, it calls it sequoias. And we're starting sampling distributions, this is chapter 8. And we'll be looking at chapter 8.1 and 8.2 today. 1 and 2, and these are on sampling distributions. Okay. And let's start off talking about the sample mean. So this semester, and it's happened more than once because this was in my notes from previously, I have opted to teach 3 stats courses. I have 3 different stats courses that I'm teaching this semester, and they're almost all filled. I just lost a few people that didn't do well on the midterm and already know it and are dropping for the drop date of Friday. I will have midterms graded before then. I'm over halfway done and I'm finishing up tomorrow. So you'll be able to see how you did on the midterm and make a decision from there. But I have 3 stats courses. And so like the mean on the midterm is different for each class. And it's how it's always going to be. I don't think I'll ever have 2 classes that have the same exact mean. When I look at grades, even at midterm or at the end of the semester, it's almost impossible because there's so many ways the mean could turn out with decimal places that getting it exactly to match is damn near impossible. But what this tells me is that the mean of a sample can take on different, not be equal to different values. And since it can be a different value, it means we can represent it with a random variable. My good old RV. And as we know, random variables have probability distributions. Okay. We're gonna use some of this in a second, but I want to just give you what we're gonna work with. Since we're dealing with mean, we always have the mean and the standard deviation. So our random variable is gonna go by X bar, because that's the mean. The mean of a sample is X bar. We use mu when it's a population, but for a sample, we use X bar. And so we're going to just describe the mean of the population. We will hardly ever know the overall population mean, but we can calculate it in terms of the samples that we do have. So I'm going to call it mu of X bar, because that's what we're basing our determination of the population mean on, is sample means. And we can just set this equal to this is going to be the mean of the population. Now, there's going to be some room for error. There's a good chance that it's not going to be exact, and we'll be covering more of that later. But what goes along with mean is standard deviation, and that's our good old sigma. And again, I'm going to use the X bar to denote that we're talking about this mean. And what this equals is the standard deviation of the population over the square root of n, where n is our sample size. And this right here, why is my phone beeping? This right here is called the standard mean of the error. So that's some technology, some jargon for, or not technology, it's some jargon for you. I'm sure they'll ask you about it somewhere, but let's just take a look at an example. I am going to simulate rolling dice. And what size did I pick? Let's come over and look at it. How many columns did I do? Let me move that to the top if I can. I believe I did 100 columns. I did do 100 columns. And if we scroll down to the bottom, look how many rows I did. I got busy. I went crazy. There are 20,000 rows, each with 100 dice rolls. So I'll come back over and write that down. We did 20,000 rows, each of 100 dice. Good old six-sided dice. Which means I have effectively simulated 2 million rolls. But I grouped them up because I wanted to show like what we look at when we're doing some sample means and stuff like that. So I'll come back over to StatCrunch. You know what? Maybe I should try to have this in a separate window and make that a smaller window. Darn you, you're in my way now. Go back like that so I can show you both. And again, I think I'm hitting you with my elbow. So what I've done is for each row, and the way I did this is I did data. If you want to try this out on your own, this is kind of cool. Data, simulate, and I did uniform for this. We're going to do a normal one, a simulation of a normal distribution in a second. But I did that. I told it how many rows and how many columns. I told it what the minimum and maximum were. And I came down and said number of decimal places equaled 0. And you know what? I'll click open a new data table just to illustrate that they are different. Oh, I had 20,000 rows, each with 100 columns. And I did a minimum of 1 and a maximum of 6. And so in this simulation, I have 5, 3, 5, 3 in the top row. The one I've already done the work on, I have a 5, 5, 4, 6. Each one has different ones. I've already done the work in this. What I did is I went, well, hell, why not? Let's just do it with you guys. Let me see how many I did it for. I did mean of 5, 10, 25, 50, and then we do all of them. So what I did is I said, okay, let's do some summary stats. And I'm going to do it on rows. And rather than columns, because I want to find the mean across the columns. Oh, I'm only going to use the first 5 columns to start off with, because the uniform is the number is the column number. And I'm going to tell it I want the mean. And I will say store in data table, so it'll make a new row. So I did mean of that. And it came over here and made row mean. And it's the mean of the first 5 squares. So 4.4 is the average of 5, 3, 5, 3, and 6. I've got 8. Another 8 is 16. Plus 6 is 22. 22 divided by 5 is 4.4. And so it did this for each row, the first 5 columns. But since I'm going to show what happens as we include more stuff, because this was dependent on n, I'm going to repeat this a couple times. And I'm going to say, well, this time I want to include, let's go up to the first 10. And we still got the same thing. I'll store that in its own row. So this will have the mean of the first 10 columns. And then I'll go do it again. I will do the first 25. And then I'm going to do 50. And finally, I'm going to do 100 because I want to show you how stuff changes as I go. And it is making these in order over here. So this is mean of 25. This is mean of 50. And this is the mean of all 100 columns for each row. Now, notice when we only did 5, we do have some repeats. I got a 4.4 and a 4.4 here. When we start doing more numbers, we will likely have some repeats. Like I see a 3.49 and 3.49 here. And that's because we only have fixed outcomes. They can only be 1, 2, 3, 4, 5, and 6. So the mean can only be so many different numbers when I'm doing 100. But this was for each sample. So I'll write over here what I was saying verbally. I have calculated. That is not how you spell calculate. Let's try this again. Of each row, this is important. I'm doing it by row, not the whole data set. For the first 5, 10, 25, 50, and then all 100 columns. So this has a probability distribution. Let's just do like a histogram of the mean of 5. Let's do that. Actually, let's do a histogram of just one column to show that it's, wow, surprisingly not even here. This should be more even. Oh, I know how to make this more even. Let's do this. I'm going to do a new simulation because it's rounding for me, and I didn't even think about that. I want to do rounding. I'm going to do 20,000 rows again. And we'll do 100 columns, and I'm going to say 0.5 to 6.5 to 6.5. That should get me the rounding that I want. Because now anything that's a 6 will be between 5.5 and 6.5. I should have checked that before I did that with you. Let's just check a histogram on a column real quick. Yeah, now this is a little more uniform, so this will work. So I'll do that, calculate the mean. I'm going to do it in, since I said that the standard deviation had a square root of the number, maybe I'll make my sample size perfect squares. So I'll go 4. And then I'm going to go, oh, I already have it open. Maybe I'll make it 9. Then we'll do 25. That one's good still. And I'll go 49. And finally, all of them. So this was the row mean of 4, mean of 16, or 9, sorry. Mean of 25, mean of 49, and mean of 100. There we go. Now it's a lot less likely that we're going to have exact same numbers. And we can still see they're all numbers between 1 and 5, 1 and 6. You can see that. Since these each have their own mean, I can find the mean of those sample means. So if I do like stats, summary stats, columns, and I just do, well, let's just do them all. Well, let's do one at a time first. And I want to find the mean and the standard deviation. Click compute, and it says, so the mean of 4 was 3.48735. And the standard deviation is 0.848436663. I can tell you the true population for dice rolls is 3.5. That's definitely what the mean is. So even just doing this sample mean, notice that a lot of these individual rows weren't anywhere near 3.5. I got 2.75s in there. I got a 1.75. I got a 1.5 down here. What does that row have in the first 4? A 3, a 1, a 1, a 1. So I have things that are far away from it, but if I do a mean of all the means, I'm really close, and that's with just a sample size of 4. What happens if I show all of them? Let's do all those means. I got 3.48, and then I go to mean of 9, and I get 3.497. It's closer. Then I do mean of 25. It's not quite as close, but it's still pretty close, closer than 4. 49 is 3.498. Mean of 100 is 3.4984. We are really, really close. That is approximately 3.5. It was so with the mean of 4, but the more we did it, the closer we got. Mean of 100 was 3.4984865. So that's to illustrate with something that we know, that the mean of dice rolls, because we have 6 answers on the dice, 1, 2, 3, 4, 5, and 6. If we add them up and all divide by 6, since they have the same probability, this is like doing that X and P of X table. Each one is 1/6. And remember, we said that the mean was the sum of X times P of X for probability distributions. So I'm adding them all up. I'm adding up 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3 plus yada yada. If I factor in the 1/6, it becomes that. And that becomes 7, 7, and 7 is 21 divided by 6, which is 18 over 6 plus 3 over 6, which is 3 1/2, 3.5. So we know what the mean is. And I wanted to show you that by doing trials, we can come up with that approximation of that mean really closely just by doing a few. Okay. And so like if you take the mean of all the sample means that you have, you can come up with a pretty good approximation. And maybe let's do a histogram on them. I did histograms on like the uniforms. I think we did 3 or number 1 already, but let's just look at the histograms there. We can see they're all, each row has or each column has relatively uniform or flat graph. But if I do a histogram on these means, check out what happens. We'll do it like that for now, where there's 1 in each one. This is the mean of 4. And notice this looks like a normal distribution, right? Oh, I did not want to do that. Clear. It looks like a normal distribution. All I did was the mean of four row, like each row had 4 rows in it. This was mean of 4. So this was the mean of the first 4 rows in row 3. This is the mean of the first 4 rows in row 7. And we just did a frequency distribution on that. And look at that. It's a normal bell curve. That's crazy. Because we started with distributions like this. We started with as far from a normal distribution as possible, and even just doing the mean of them and grouping them in terms of 4, I've got a normal distribution of what the mean should look like. And it should get only better. Right now it goes from 1 to 6, and we got a height like that. Let's see what happens when we go mean of 9. It's still bell curvy, but not quite as much. Like a little steeper in the center. Notice it doesn't go out as far. It only says 2 to 5, a little under 2 to a little above 5. If I go mean of 25, we're now back into looking like a good bell curve. But now it's even narrower. It's the lowest mean, or the lowest thing is above 2. The highest mean is below 5. And if I go mean of 49, it's squeezing in even closer. Now it's not greater than 2, it's greater than 2.5, less than 4.5. If I go the mean of the full 100, my distribution is barely below 3 and barely below 4, and yet it remains a normal bell curve. That is what that whole mu of x equals mu of population. This is what it's showing us. The mean of our x bar the mean of our samples, the mean of our sample means. Is equal to the mean of the population. And we saw that the deviation was the deviation of the population over the square root of n. Which means as n goes up, like when n equals 1, sigma x bar is just sigma population. If n equals 9, I've got sigma population over the square root of 9. Sigma x bar is 1/3 the standard deviation. Oops. I'm trying to squeeze too much in one spot. Let me write it down below. When I do n equals 9, I have the standard deviation of our sample means is 1 over the square root of 9 sigma population, which is 1/3, which means it's smaller standard deviation than the population. Very good. Get that a little bit off screen. When I do n equals, I'll jump up to 49. I don't need to do the 25. I think showing a few examples. Sigma x bar is sigma population over square root of 49, which is 7. So this is 1/7, which means even smaller. And remember how we use those standard deviations. When we're drawing the bell curve, and we obviously have going the other way, -1, -2. The smaller these sigma are, the narrower that gets. But the mean doesn't change. It's going to have to go a little bit higher. And then it gets even taller. Oop. It's still always centered around the mean, but it gets narrower and taller like this is. If I re-show this as showing them all on the same screen, I wonder if it'll keep the same layout. Oh yeah, let's do this. Nope, let's start at 1. We'll set the bin width on each of them. Maybe I'll make it smaller. Let's go 0.05. Because I want all the graphs to look the same. At least have the same basis. Okay. This is what I was talking about how notice it gets narrower and narrower and narrower. Why is it not showing all the way up? Oh, because the later ones don't have high numbers. Oh, okay. Either way, we can see that the graph gets narrower and narrower and narrower by doing it. Okay. So what I just drew on the screen right there, I can put into words. As n goes up, which means more in our sample, the standard deviation goes down. Which means it's less spread out. That's what it shows on the screen, which means less dispersion or spread. In our results. And we can see that the dispersion goes from 1 to 6 with the low number n. And when n gets up to 100, we've got a very narrow dispersion. It's only going from like 3 to 4. Whereas it was going from 1 to 6 when we were down at mean of 4. So there's spread changes. Which means the likeliness the likelihood, I think is a better word, the likelihood of having an extreme mean goes down. Outcome, I should say. And just to kind of show that, I'm going to do like I'll do the min and the max for each of these rows, or each of those mean. So the 4 went from 1 to 6. 9 goes from 1.5 to 5.4. The mean of 100 was 2.7 to 4.14. While the mean of 4 had some extreme results like a 6 and a 1. So apparently somewhere on this table, the first 4 numbers were a 1. The first 4 columns had our 1s in the rows. And somewhere else in the table, the first 4 had a 6. But as we did more and more, this changes, and the likeliness of having those extreme responses goes down, which is kind of cool. Let's look at another one. So I just showed you the uniform distribution. So the uniform distribution only having n equals 4 for individual sample means led to a normal distribution for the mu of x bar, where it did the mean of the means. Mean of means. Oops. Mean of sample means. So that's with a uniform distribution. What about a normal distribution? What if we start with a normal distribution? Let's start with the normal one. Let's use the IQ test. The IQ test has a mean of 100 and a standard deviation of 15. This is for the entire population. Let's simulate that here. I'm going to do data. I'm going to do simulate. I'm going to do normal distribution. I'll do the same thing. I'll do 20,000 rows. I don't have to do them by hand, so it's easy to do a bunch. We'll do 100 columns. The mean is 100. The standard deviation is 15. I'm going to tell it not to round because I don't think the IQ is rounded. And we'll open it in a new data table so we can see it fresh. So like this is, if I do the first four of this first group, it's 108, 86, 94, 85. 85 is kind of a little bit lower than I expected. It's one deviation marker, but let's go through and do that distribution. Well, first off, let's look at the histograms of some of these. They're already normal, right? As they should be. It's a simulation of a normal distribution. It should be that. Ooh, I could change the name. I didn't want to do that. Okay. Now let's do that same process that we did before. We're going to do the mean of some rows. So each row, I want to do the mean of the first four. And I'll store it in the table. Then we'll only do a couple. I'll do mean of the first 25. And then we'll jump up to like 81. Let's go to full 100. So this was mean of 4. Mean of 25, mean of 100. And now we can look at the mean of each of these columns. So we're taking the mean of means. And we'll look at the mean and standard deviation there. And maybe I'll throw in min and max so we can just see it all in one set also. So when we did 4, well, notice in all of them, they're all pretty close to that 100, right? They're all really close to this mu equals 100. So again, we can see that our mu of x equals, or is approximately equal to mu of our population. Standard deviation, the mean of 4. That means n equals 4. And if I do sigma x bar equals sigma population over square root of n, I get the sigma for 4, mean of 4 of them, is equal to the sigma of the population, 15, over the square root of 4 is 2. 15 over 2 is 7.5. And look at that, I'm pretty close to 7.5. If I did even more rows, I'd get closer. The mean of 25, if I do sigma where x is 25, I've got 15 over the square root of 25, which is 15 over 5, which is 3. And look at that, really close to 3. And if I look at the standard deviation there, again, on that one, we're doing sigma for 100. I've got 15 over the square root of 100. Square root of 100 is 10. 15 over 10 is 1.5. And look how close I am to 1.5. That's kind of cool. That's actually really cool. And we can just do a quick histogram on those as well. And show that those have normal distributions as well. And just like we see over here on this table, I'm going to widen this up for a second so I can show both. I've got the min and the max listed. When I did mean of 4, I had 74 to 132, which it's not quite as wide as I would expect for maybe just doing a mean of 1. But notice that as n goes up, that min gets higher and that max gets lower. We're squeezing in on the graph, where each of the extreme values is getting closer to the center value. When we have mean is 100, this is 93.73, which is just a hair over 6 away from 100. And 105.4 is under 6 away from 100. So these are all like they're only 6 away, whereas this is 32 away. So the bigger the n, the closer, the tighter we focus in on the actual mean of the population, which is handy if you don't know the actual mean of the population. If you know you have a normal distribution, if we know the distribution is normal, as n goes up, we get a tighter fix or a tighter window on what that actual mean is.
Professor Jones?
Yeah.
Well, we can't
I'm
see what you're
hiding the
writing.
text. Let me fix that. That's what you're about to say, right?
Yeah.
Yeah, my bad. Thank you. As soon as you spoke, I looked up and realized what was going on. If we know the distribution is normal, as n goes up, we get tighter window on, I got sidetracked in my thoughts, which gives you time to write what I was saying down while I erase this and put something better in. On the true mean, and then here we're talking about the distribution of the mean, of a sample mean. But I just gave you 2 scenarios. I did a uniform distribution, which is the most farthest away from a normal distribution. And then I did a normal distribution and showed it. It turns out, regardless of what the underlying population distribution looks like, the sampling distribution of the sample mean, it's important that we're talking about the sample mean, is approximately normal. And I'm going to add a little caveat for large enough n. And depending on the book, the general rule of thumb for large enough n they've kind of narrowed it down to n being greater than or equal to 30, but n greater than or equal to 40 is also a good way to look at it. And we saw that on the uniform. It was even pretty uniform at 4. But when we had like mean of 50, it was definitely looking pretty bell-shaped. And this thing that I got in gold right here, this is called the central limit theorem. Regardless of the underlying population distribution, if we look at the sampling distribution of the sample mean, it's approximately normal for large enough n. If we combine that with what's in pink, where we didn't know the population, if we don't know the mean of the population, we can approximate it by doing this sampling distribution of the sample mean. That's pretty cool. Because that means if we do enough surveys, we can break we can do like little subsamples of who we sampled and find the mean of, like, if I ask 200 people, I could break it up and do like 10 people in each group and have 20 groups. Or I can find different combinations where they overlap a little bit, but like they're like not the same people in each group. But like maybe 1, 2, 3, 4, 5 is in the first group. And then maybe 5, 10, 15, 20, 25. Individual number 5, 10, 15, 20, 25 are in the next group. The 5 was in the first group and the second group. But as long as I'm making these different groups, I can get an idea of what the sample mean is for each group, and doing the sample distribution like this, I can get a good idea of what about what the mean is for the entire population. That's what they do when they do all these surveys and shit, or taste tests and all this consumer surveys online, things like that. They find what the few people think, or enough people think. They can't survey everybody, but they survey enough people that they can get a relatively good idea of what the majority are going to think with some margin of error. Pretty cool. I'm going to bring this over and look at like some problems from our homework real quick. Chapter 8. I wanted to look at 6 and 10 with you. So it says determine mean of x, or the sampling district, or determine mu of x and sigma of x from the given parameters of the population and the sample size. So the information they gave us guess I need to do that. Where'd it go? Oh, let me look at it again. From the information they gave us, we want to figure out what those are. So number 6, and your numbers will vary. They're telling me that the mean is 31, and this is the mean of the population. Sigma of the population is 9. And our sample, that looks bad. And our sample size is 30. We need to find mu of x bar and sigma x bar. Well, this one is the mean. The mean of the sample should be equal to the mean of the population if it's known. And this is going to be the standard deviation of the population over the square root of n. So we should have 31 here. And this should be 9 divided by the square root of 30. And I don't know what that is, but I know my calculator does. My calculator knows a great many things, or at least it can figure it out. It's one smart cookie. 9 divided by square root of 30. I'm getting is, how many decimal places do they want? They didn't say. Let me just put in the first number first. 31 is my mean. To 3 decimal places, my calculator is telling me 1.643. Easy as that. I'll jump to another question that's a little bit harder. We'll go up to 10. And I already answered one of the questions because it's just asking question about the sample size. But let's read the question. The shape of the distribution of the time required to get an oil change at a 15-minute oil change facility is unknown. However, records indicate that the mean time is 16.4 and the standard deviation is 4.6. Complete parts A through C. To compute probabilities regarding the sample mean using the normal model, what size will be required for, or what size sample would be required? And I had told you that we wanted to aim for, it used to be they'd say n is 40, now they're happy with n is 30. N needs to be greater than or equal to 30. I clicked it, it said yes, it said good job. And now it says, what is the probability that a random sample of n equals 35 oil changes results in a sample mean time less than 15 minutes? So let's unpack that a little bit, see what's going on. I know, this is problem number 10. They told me that the mean time was 16.4 and the standard deviation was 4.6. And they're giving me a sample size of n equals 35. And they want to know what is the probability that the sample mean time will be less than 15 minutes. I'm going to go look at StatCrunch real quick and work this out over there. So we know this gets to be a normal distribution model. So I'm going to use the normal calculator. And I'm going to put in mean of 16.4. And I'm going to put in what they gave me, 4.6. I'm going to say probability is x is less than 15. There's a good chance you'll all do this. So I did mean is 16.4. Standard deviation equals 4.6. And I did the normal calculator and I found that this was 0.38043.146. I'm going to come over here and answer that in 0.3804. And it's going to tell me I'm wrong because I did not factor in the square root of n part. It's wrong. To do it right, I can keep the 16.4, but sigma's got to be 4.6 over the square root of 35. So I don't know what that is right now, but it needs to go here, and I can throw it in the calculator and figure it out. And I'm going to put as many decimal places as I can because I don't know where it's gonna, the last digit will affect the answer. Now I'm going to do probabilities x is less than 15. And I'll click compute, and look at that, it's a lot lower. And now when I come over here and do that, not 3.8, it's 0.3. It's even shifted a decimal place. And rounding to 4 decimal places would be 0.359. Okay, so pay attention for that. If you get it wrong, make sure you divide it by the square root of n. And I deliberately made that mistake to show you what's going to happen. And then it says, okay, what do we got here? What magic mojo are they doing now? Suppose the manager agrees to pay each employee a $50 bonus if they meet a certain goal. On a typical Saturday, the oil change facility will perform 35 oil changes between 10 a.m. and 12 p.m. Treating this as a random sample, there would be a 10% chance of the mean oil change time being at or below what value. This will be the goal established by the manager. So like maybe he gives the employee a bonus, and because he's going to promote an ad that says, we'll have your oil change done in this time or less. So like we're still doing 35 oil changes. None of that other information's changed. All we're changing is our simulation. We want to make this 10% because we don't know what X is. We don't know what that value is, but we want to aim for a percentage, and 10% as a decimal would be 0.10. And so maybe this isn't the ad. He wants, the quicker people get done, I'll show you an ad version of this in a second. He wants employees to get the oil change done faster, because if it's done faster, he can do more oil changes per day and bring in more money. So he's going to reward them if they get it below a certain time, but he doesn't want to pay too many people or give out too many bonuses. So he's only going to give out the bonus if it's a rare event. And so he's going to say 15.4 minutes. Now, before I go to the next question, I'm going to go back and look at this simulation thing and go, okay, what if he's wants to tell customers, he knows it's about 16.4 minutes or less. And he wants us to tell customers, if you come to us, we'll get your oil changed in 20 minutes or less. What would 20 minutes or less look like? What would our Well, I would do B most of them. So he could get away with it. Maybe he wants to go with a smaller value. Maybe he wants to say 19 minutes or less. That's still pretty good. What about 18 minutes or less? 18 minutes or less is pretty good. What about 17? 17's too small. So he might go like, maybe he doesn't know what this value is. And he doesn't want to do this check thing like this. What if he wants to go just like, if it's not in under, you know, like they used to do ads, your pizza delivered in so many minutes or it's free. This will be like, maybe your oil change is free. And so if it's not done in so many minutes, and he doesn't want that to happen very often. So he's going to say like, I want to find the time limit where like maybe only 2% of them don't do it. So I'm going to say like 90 or like say 5%. I'll put 0.95. And now if I look at it, 17.67 minutes, 68 minutes, 95% of them are done. So maybe he'll go up to 18. He'll say if it's not done in 18 minutes, your oil change is free. Because he doesn't want to drop down to 17. He wanted a cutoff. 95% is his cutoff. If he goes down to 17, he's going to have to pay 23%, 22%. Everybody that's longer than that, give it to him free. If he goes with 18, he doesn't have to give out hardly any. He's giving out 2% of it. So there's a couple ways to look at that one. But that's how we can use this kind of thing. And that's the type of problems you'll see in the homework. I want to go on to sample proportions. This is 8.2. It's on sample proportions. And if we're trying to find the proportion of people who weigh, let's say between find the proportion of adults. Let's go with adults who weigh less than 105 pounds. And they want to know for the population. Everybody, which would mean finding and weighing every adult in the world. And that's just if we're looking at current times, right? Which is realistic. We probably shouldn't look at like the weight of people 200 years ago when we didn't have mass production of Twinkies and shit like that. So maybe we're looking at current times, but still, finding the weight of every adult in the world is not doable. So we can't really find the proportion of adults that do that realistically. This is impossible for most circumstances for a population. For most types of questions, not just weight, but any types of questions of a population. But finding the proportion in a sample is pretty fucking easy. It is super easy. How many said yes? How many said no? How many weighed 105 or less? How many weighed over 105? It's clear cut, easy to calculate. And we know we've done this before. It was X over N. We did this. The proportion was effectively, remember, proportion is very, very similar to relative frequency. And we calculated that by doing X over N. X was the people that had the trait. N was the number of people in the population. we're going to call this P hat. P hat. When we do this for a population, or when we calculate the proportion for a sample, and want to estimate the population proportion, P hat is called a point estimate. Point estimate. It's an estimate of the overall proportion in the population. Oh, don't go too far off the screen. But depending on which group of people I ask, if I go to like a gym, maybe not a gym, maybe if I ask people that are jogging, let's go with joggers. Joggers tend to be really lean. If I ask a jogging club, they might have a much lower estimate than if I go to like Weight Watchers for like asking weight. So the point is P hat is different for different samples. Which means it changes and it's a random variable. That's not what I wanted to change. I want to change that one. I actually didn't. No, I'm not done with that one. It's a random variable, and so again, it has a sampling distribution. Sampling distribution of P hat. The proportions. And so like the probability distributions, again, we need a mu and we need a standard deviation. We're going to call it mu of P hat and sigma of P hat. Actually, no, I don't want to do that. I want to just call it mu of P, and I'll get back to you on whether we use hat down there. But I think it's just going to be the population. So P. The mean of the population, if we do all those, well, it is P hats. It should just equal P hat. It should equal our proportion. We'll just put P. And then standard deviation, gotta go back to my pin. Standard deviation, it's got some fun shit in there. It's got P times 1 minus P over N. That's kind of like in parentheses. Then you take the square root. Now we did show for a mean sampling distribution of a sample mean that it approached approximately normal relatively quickly for any distribution. And so we just said n greater than 30. Here we want to guarantee approximately normal here. We want two things. A, n times p times 1 minus p needs to be greater than or equal to 10. And B, I want n to be less than or equal to 0.05 times big N. Where we know this one, this is sample size. And you know big N, but it's been a while. This is population size. So the sample size is less than 5% of the population. Seems like a weird requirement, right? It seems like, well, why can't we go like 6% or 10%? That's just what these geniuses came up with. Guess what? We're going to still use stats, calculator, normal. Well, those calculations need to be done by hand. As in sigma was p 1 minus p over n and then square root. You'll need to do that on a calculator, and you probably need to do np 1 minus p is greater than or equal to 10 on a calculator as well. But after that, everything else is in the stats calculator normal. And I'll show you. We're going to do a question. We're going to do number 15. So this is from our homework set, number 15. It says a simple random sample of size n equals 200. I'm going to write this down. Is obtained from a population whose size is 30,000. And whose population proportion is 0.6. Describe the sampling distribution. Choose the phrase that best describes the shape of the sampling distribution. And all of these questions have to do with checking these comparisons. So it looks like that's what we need to start off doing. Let's figure out what n times p times 1 minus p is. Because we want that to be greater than or equal to 10. So I have 200 times 0.6 times 1 minus 0.6, which is 200 times 0.6 times 0.4, which is 200 times 0.24. And that should be 48, which is definitely greater than or equal to 10. So bingo. Now we'll check, is n less than or equal to 0.05 of big N? Big N was 30,000. I've got 0.05 of 30,000. I think it's 150, but I'm not good with numbers that big in my head, so I'm going to use a calculator. Nope, I was wrong. It's 1,500. Look at that. 1,500. And so that's my right side. This is my right side. My left side is 200. So I've got, is 200 less than or equal to 1,500? Yes, it is. Winner, winner, chicken dinner. This means that this is approximately normal. And I need to pick the one that says that. Both B and C say approximately normal. They both say n less than 0.05 n. And it looks like the only difference is this symbol here. I want the one that says greater than or equal to, so I got to pick that one. Describe the mean of the sampling distribution of p hat. Well, we got done saying that they're probably going to ask us standard deviation, so I'll rewrite the formulas real quick. Mu of p hat is equal to p. Sigma of p hat equals square root of p times 1 minus p over n. So let's take a look at our group. P was just 0.6, so mu of p hat for us is 0.6. Round to 1 decimal place, yeah, of course, it's already that. Now they want us to do the standard deviation, so this is going to take a little bit of work. Undo. I got 0.6 times 1 minus 0.6 over n is over 200. And I know that top part was 0.24. I just did that earlier. 0.24 over 200. I'm going to calculate this in a calculator. I'll do 0.24 divided by 200. So I've got the square root of 0.0012. And then I'll take the square root of that number. And I'm going to get 0.034641016. Oh, they wanted 6 decimal places. Look at these tricky bastards. 6 decimal places. What the hell? Maybe I should count 6 before I start going crazy. That's 3, that's 6. So up to the 1. Bam. What is the probability of obtaining x equals 126 or more individuals with the characteristic? And then that was kind of nice. Look what they tell us. They actually say, what is the probability that p hat is greater than or equal to 0.63? Well, I've got the mean and I've got the standard deviation already. I can go back over to that normal calculator and I can put that in. What did you do? There we go. Stats, calculators, normal. I'm going to set my mean to equal 0.6. I'm going to set my standard deviation to equal the 6-digit number that they wanted. They wanted to do 6 decimal places, so I'm doing all 6. And I'm going to say probability that x is greater than or equal to 0.63. And I get 0.193238. So we're back to that normal calculator again. It's a good thing we learned how to use that for our midterm, right? They want 4 decimal places here, which is 0, 0.1932, and I got to round down because the next decimal place is a 3. Now they want us to do it again. The p hat is less than or 0.52. It doesn't look like anything else has changed, so let's just go in here and say less than 0.52. So I wrote that all down over there so I can come back over the question. To 4 decimal places, I've got 01046, which is 0105. I got to round up, right? Where's my mouse? There it is. And that's it for that question. So that's the kind of stuff we're doing here in chapter 8. We're making it so that we're learning how we can use sampling of distribution, sampling of like samples, and find means or proportions and use that to find information about the population, which is what we're going to start doing hypothesis testing with in chapter 10. Chapter 9, we got some more stuff we got to cover first. But I think we start doing it in chapter 10. That's it for today. How's that for beautiful? Any questions? Nope. All right. I will see you all later. Have a good day.
Have a good day, Professor Jones.
You too.